In this paper, we introduce hybrid imitation learning for dynamic athletic control. We tackle the challenge of training a unified controller capable of performing diverse and dynamic athletic skills across challenging environments. Due to the scarcity of motion capture data for athletic interactions such as parkour, our framework leverages online videos to learn diverse parkour stunts. We extract human motion using off-the-shelf pose estimation algorithms. Scene geometries are manually constructed for each motion to ensure alignment with the simulated environments. We train a physics-based motion tracker for each sequence, effectively reducing artifacts in the reconstructed motions and improving their physical accuracy. Our dataset contains 19 reference motion clips, along with the corresponding obstacles, collected from YouTube. Using this dataset, we train our parkour controller to traverse sequences of obstacles in novel configurations. We also apply our method to a heading control task, where the character must move in a target direction while following a target-facing direction. We use the sword and shield dataset, which includes locomotion and combat motions with strong directional cues. To train these versatile controllers, we propose a hybrid imitation learning framework, which is implemented through parallel multitask environments. This framework includes two modes, motion tracking and adversarial imitation learning. In the motion tracking mode, the controller is trained to replicate basic skills by imitating individual motion clips in the dataset. The tracking reward is computed by minimizing the differences between the simulated and reference motions frame by frame. In the adversarial imitation learning mode, taking parkour as an example, the controller is trained to clear sequences of obstacles by composing and adapting the skills in the dataset. The task reward encourages the controller to follow sequential target goals effectively. By training the controller on both tasks simultaneously, HIL learns a diverse set of parkour skills while also learning to compose and adapt various skills to clear diverse obstacles and novel environments. In our experiments across diverse environments, we show that our hybrid imitation learning method is able to improve motion quality, skill diversity, and robustness compared to prior methods. We apply our method to a heading control task, where our HIL policy achieves robust alignment with both heading and facing goals while maintaining natural, lifelike motions, leveraging a diverse set of skills. For the heading task, we compare our method with AMP, ASE, and masked mimic. AMP achieves high task returns, but its motions are often repetitive and less natural. ASE produces more lifelike behaviors, but struggles under certain conditions, resulting in weaker task performance than AMP. Masked mimic fails to generalize and typically falls when the target heading is out of distribution from the reference data. In contrast, our policy is able to closely follow both heading and facing goals, while maintaining natural motions. Furthermore, our method is able to mitigate mode collapse leading to a wider range of behaviors, such as diverse sword swings. For the parkour task, we compare against the same baselines. AMP often stalls in front of obstacles and then attempts to walk around them. ASE, trained only with discriminator rewards, fails to interact meaningfully with obstacles and typically gets stuck during pre-training. Masked mimic collapses after the first obstacle since it is trained solely through motion tracking. By combining motion tracking with adversarial imitation in a unified framework, our HIL policy avoids these issues. Our ablation studies highlight the importance of each framework component. Task reward with warm start leverages our first stage motion tracking policy as initialization. Controllers trained only with a task reward focus on task completion and produce unnatural behaviors, prioritizing speed over realism. AMP with warm start is equivalent to HIL without the tracking mode, and it suffers from severe mode collapse, repeatedly applying the same skill across different contexts. Removing the discriminator, without D, leads to unnatural behaviors when clearing sequences of obstacles. Without perturbed state initialization, without PSI, the controller becomes less robust to state deviations, leading to less effective composition and sequencing of different skills. Excluding scene information from the discriminator, D without scene info, can lead to unnatural interactions, as the controller struggles to apply appropriate skills for specific obstacles. Our method demonstrates robust performance across a variety of test cases. In this example, the controller adapts the same parkour skill to clear obstacles with randomized characteristics beyond the training data. The controller also demonstrates robustness to unseen obstacle placements when sequencing multiple skills, showcasing its ability to generalize to novel scenarios. In addition, the controller is capable of clearing significantly longer obstacle courses, far exceeding the lengths of sequences encountered during training. To further demonstrate the generality of our method, we train a policy capable of performing both dynamic parkour stunts and everyday interactions such as sitting on a chair. While our method generates lifelike parkour behaviors, occasional artifacts, such as unnatural recovery motions, can still occur. Additionally, the controller is trained on linear obstacle sequences, which limits its ability to navigate more complex and dynamic environments. Expanding its capabilities to handle general scenes remains an avenue for future exploration. This work introduces a hybrid imitation learning framework that combines motion tracking and adversarial imitation learning. With this framework, we train a unified controller capable of executing diverse parkour skills in novel environments. Beyond parkour, this framework may be applied more broadly to other human-scene interaction tasks, paving the way for more versatile and general-purpose controllers for physics-based character animation.